guys, in this video we're going to go over diffraction gradients. Okay, so diffraction gradients are actually a really nice little topic, but some of the questions can kind of trick you out. So what is a diffraction gradient? A diffraction gradient is very like a double slit, but instead of having two holes that light can come through, a diffraction gradient has loads and loads and loads of little slits on it that the light can get through. And then that little d there represents the distance between each of those tiny little slits in the diffraction gradient. Okay, n is our order number, and this is the wavelength of light we used, and sine theta represents the angle between the central maximum and our first order, right? So what does that mean? What does it look like in a picture? So let's say our light with a certain wavelength is going to shine through our diffraction gradient. We're going to get a screen with a pattern on it. We know we're going to get a central maximum. So if we call that central maximum, it's going to be our order number 0. So that central maximum, we get our first bright spot, we call that order number 0. Then we know we're going to get those alternate bright and dark fringes on our screen. Either side of that central maximum is called the first order. Either side of the central maximum is called the second order. Either side of the central maximum is called the third order. Okay, so again, we know on the screen what we actually end up seeing is those peaks, right? We have our central maximum, and then you have your fringes on either side. Okay, so again, D is the separation between the slits. Sine theta then, so sine theta, what that represents is the angle between the 0 of order. So we do a dotted line from our diffraction gradient 0 order. Sine theta is the angle between it and that order, order 1. Okay, or it could be the angle between order 0 and order 3. That's that angle theta there. Okay, so let's look at our question. Question says there's 600 lines per millimeter. 600 lines per millimeter isn't the distance between the two slits. 600 lines per millimeter tells us n. So n is there's 600 lines in 1 millimeter. So n is there's 600 lines inside 1 millimeter. So again, if I have 1 millimeter, there's 600 of those slits on it. Okay, but I want to know the distance between the slits. To calculate the distance between the slits, you need to know that you have to do 1 divided by n. That's not on your data sheet, it's something you need to know. Okay, we know that has to be in meters. So the first thing I would do is convert this into meters. If there's 600 in those tiny little lines inside 1 millimeter, if I have 1 meter, obviously there's going to be more. There's going to be 600,000 lines in that 1 meter, right? Because if there's 600 in just 1 millimeter, if I have a meter, there's going to be 600,000. So to calculate what D is, the separation between them, we just do 1 over 600,000. And that's going to give us what our D is. So again, 1 divided by 600,000 is equal to 1.67 times 10 to the negative 6 meters. So that's our value for D. Okay? So I want to know what's the angle between the 0th and the second order. So we're looking here is we're not looking for those angles of theta. We're looking for the angle between the 0 and the second order. So 0 and my second order. So I'm looking for that angle there, theta, between the 0 and the second order. Okay, so again, just to highlight that a bit better, we're looking between the 0 and the second order, what that sine theta is. So what I'm going to do is n sine theta. I'm looking at the second order, so n is 2. 2 times the wavelength. The wavelength is 500 nanometers. So 500 times 10 to the negative 9 is going to equal D, which is 1.67 times 10 to the minus 6 multiplied by sine theta. So if I want to find what sine of theta is, I just have to do 2 times 500 times 10 to the minus 9, and I have to divide by 1.67 times 10 to the minus 6. And that gives me my sine theta, which is going to be 0.599. So to find what theta is, I just have to take inverse sine. So I'm going to shift sine or inverse sine of that previous answer to find out what my angle theta is, and it comes out there at 36.8 degrees. So that's the angle between my 0th order and my second order. That angle in there is 36.8 degrees. Okay. Okay, next question said, what is the maximum number of fringes on the screen? Okay, so I want to see how many of these bright fringes can I get on the screen. So I want to see how many of these bright fringes I can get on the screen, and hopefully you're seeing that angle of theta is increasing, 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 increasing. So the maximum is going to be when theta is equal to 90 degrees. So I'm going to do the maximum when theta is equal to 90 degrees. Sine of 90 is 1, so what I've got now is d is equal to n times the wavelength. So again, d we said is 1.67 times 10 to the minus 6 is equal to order number times the wavelength, which is 500 times 10 to the negative 9. So to find what n is, all I have to do now is 1.67 times 10 to the negative 6 divided by 500 times 10 to the negative 9 to get my order number, which comes out at 3.34. Okay? So clearly you can't have 3.3 fringes. So the order number there is 3. So what I'm saying is actually the maximum number I can get is only up to 3. So I get 3 on one side and 3 on the other. That's the key thing to remember. A lot of people leave it here and think you see 3 bright fringes. You don't. The order number is 3. Then a lot of people think I just multiply by 2 and I get 6 bright fringes. But it's not, because you forgot 0. So it's 1, 2, 3, 4, 5, 6, 7. It is going to be 7 bright fringes. Okay? Or you could do 2 times the order number plus 1. But you can't forget that central maximum.